I'm now going to take a bit of a departure from the usual calculus topics that you're used to seeing. You've seen limits, derivatives, integrals. We're now going to kind of come back to some stuff with limits, and we're actually going to kind of look at a few calculus-related things in a foundational sense. In fact, when you take a course, usually in your first real analysis course or here at UTSA, Foundations of Analysis, you actually start here with sequences, and then you build up the rest to everything that you have already known. So we're going to begin our discussion on what sequences are, how to operate with them. And this video, we're just going to talk about the basics. So all a sequence is, and this is just the basic working definition, it's just a list of numbers, an infinite list of numbers. Okay, it's really a function on the natural numbers. Okay, so if we write a sequence, okay, like this, okay, we have this thing here, a sub n. Okay, this is indexed by an integer, really a natural number n, and we have a rule. So here's this first one here. We have this sequence, an, it's defined as n over 2n plus 1. So what does that really mean? Given an n, we're just going to plug in, right? We take the index number divided by 2 times the index plus 1. So let's go ahead and figure out what the first 6 terms are. That's just our first part of our question here. So let's look at the first 6 terms of this sequence. So if I want, say, a1, okay, well, we're just going to plug in n equals 1 into our rule, okay? So we have 1 over 2 times 1 plus 1. 2 times 1 is 2, plus 1 is 3, so the first term is 1/3. Okay. Now what's next? Okay, well, a2, our second term. Well, now we're going to plug in n equals 2. Okay, it's just a function. That's all it is. So 2 over 2 times 2 plus 1. So we have 2 over, I believe that's 5. Okay, and then you can figure out the pattern here. Okay, when we plug in n equals 3 here, we'll get 3 over 7. Oops, sorry, that should be a 3 on top there. Okay, and then for n equals 4, we have 4 over 2 times 4 plus 1. That's 4 over 9. And I'm pretty sure you can guess the pattern here for 5 and 6. But let's just write it down. 2 times 5 plus 1, that's 5 over 11. Then a is 6. We have 6 over 2 times 6 plus 1. That gives us 6 over 13. And you can probably figure out the rest, 7 over 15, 8 over 17, so on and so forth. Okay, now we have the second part here. Does this sequence appear to have a limit? Okay. So now the question is, what do we mean by limits? Well, in the same sense that when we talk about limits of functions, okay, we can talk about limits of sequences. Okay. So let's kind of give ourselves a bit of a working definition here, okay, for the limit of a sequence. Okay. So the limit of a sequence, the limit L of a sequence is the limit then goes to infinity of the rule an, if it exists. Okay, if the limit exists, okay? So we're going to have to go back to some Calculus 1 knowledge, okay, from those first few weeks of Calculus 1. Okay, remember when we talked about limits and everything, okay? We have to still use those, okay? Of course, we did talk about limits a bit in improper integrals, so if you are still shaking on those, please refresh yourselves with the basics of limits. So let's take a look here. We want to examine the limit as n goes to infinity of n over 2n plus 1. That's our rule for our sequence. Well, now let's think about this, okay? I have something of a polynomial type over something of a polynomial type. The numerator is linear. The denominator is linear. Okay, so I'm going to go ahead and divide out the highest power that appears. That's going to be my n. So I'll go ahead and write that step out here. Okay, of course, if you know the shortcut, it's equal heavy. You probably already know the limit, but let's save that for those that may not remember, okay? So let's divide top and bottom by n. So I have n over 2n plus 1 over n. All right, in the numerator, we just have 1, and in the denominator, we will just have a 2 plus 1 over n, just how fractions work. And notice that in the bottom, right, 1 over n goes to 0 as n goes to infinity, okay? That's one of our basic limits that we have, right? So let's write this down here, okay? 1 over n goes to 0 as n goes to infinity. So the whole denominator will go to 2. So what's our limit here? 1/2. Okay, so that's our limit L, okay? The sequence has limit 1/2. And that's it. Nothing really new here, right? Okay, a sequence is just a function of the natural numbers. You just plug in, get terms, okay, whoop-de-doo. And then for the limit, you just do the same thing that you did in calculus 1. Okay, you're taking a limit to infinity, all right? So let's go ahead and look at our next one here. We want to now find the first 8 terms of this sequence. And now our sequence is an, which is equal to sine of n times pi over 2. Okay, so we're thinking about a unit circle here, okay? Our basic angles on the unit circle. Let's go ahead and kind of refresh ourselves what we're doing here. So I'm going to go ahead and draw a circle. And remember that for our unit circle, the sine of an angle is the y-coordinates, okay? So let's think about what's happening here. When n is equal to 1, okay, let's actually write that down. We want sine of pi over 2. Well, what is sine of pi over 2? Well, if we look on a circle here, let me mark it in red here. Sine of pi over 2, that y-coordinate is 1. Okay. Now what about a2? That's going to be sine of 2 pi over 2. Well, 2 over 2 is 1, so we have sine of pi. So let's just write that down. Sine of 2 pi over 2, which is sine of pi. All right. Mark that on our circle. That y-coordinate is 0. And now how about a3? Sine of 3 pi over 2. Okay, sine of 3 pi over 2. We mark that in our circle that's down here. And so what is the sine of 3 pi over 2, everyone? -1. Okay. And then we have a 4, which is sine of 4 pi over 2. That's sine of 2 pi. You know what? Let's just be kosher here. 4 pi over 2. And mark that here. Well, sine of 4 pi over 2, sine of 2 pi. That's a positive. Well, that's a 0. All right, now let's keep going because we need 8 terms, okay? We don't really see a pattern here. We have 1, 0, -1, 0. Okay, now let's take a look here. A5, that's going to be sine of 5 pi over 2. Well, sine of 5 pi over 2, okay? Well, 5 pi over 2, remember, think about the unit circle, okay? One revolution, one lap, one rotation is 2 pi radians, 360 degrees. So I have 2 pi, but then I have a pi over 2 left over. That's already at this point that I've marked off here. Okay, pi over 2 and 5 pi over 2 are coterminal angles. Remember that from pre-calculus. So we have the sine of 5 pi over 2, and you can check this on your own. 5 pi over 2, sine of 5 pi over 2 is 1. And now you'll see something funky here. Sine of 6 pi over 2, okay, that's 3 pi. So we already go 2 pi around, that's one whole lap. And then we got to go the extra pi radians, so that's sine of pi, which we have up there is 0. All right, now let's finish this out, and you'll probably see something weird happen here. If I can find my cursor, scroll. There we go. Okay. A7 is sine of 7 pi over 2. If you use the same reasoning in the picture, we get a -1 here. That's not good. All right. And come on. This is fine. Sine of 8 pi over 2. You'll see that that's 0. So take a look what we have here. Okay, let's try to give a visual picture here. Let's call this baseline our 0. So we have 1, 0, -1, 0, 1, 0, -1. You see how it oscillates, right? If you graph sine of n pi over 2 in terms of discrete points, you see that they all wiggle, okay? And the idea here is we're looking for the limits as n goes to infinity of sine of n pi over 2. And the thing is, that limit does not exist because we have this oscillatory behavior, okay? This does not exist. Okay? Now the question here is why? Why does the limit not exist? Okay, well, let's think about it, okay? Sine of n pi over 2 oscillates. It oscillates between 1 and minus 1, okay? It doesn't settle, okay? Like in that first example, we could easily see that all the terms were approaching the same number. We were approaching 1/2. But in this one, we're just going to wiggle. 1 minus 1, 1 minus 1, 1 minus 1, okay? We're still going to get the 0 in the middle, but we're not settling down on one value. But it averages out to 0. That's not really what limits are. We need it to settle on one single value. So that's why the limit does not exist. Okay. All right, we got 2 more here. I have now a recursively defined sequence, and we want to figure out if this has a limit, okay? We're going to first explore by looking at the terms of the sequence, okay? Whenever you're looking at a sequence for the first time, explore, okay? Explore. Now, you folks that know computer science, you folks that know programming language, you know about recursion, right? Going down the stack, you're calling a function again and again. Here's the difference between this one and the ones that we've seen before. In the previous ones, let's go back. Okay, in this one and the previous, we have explicit rules for our sequences. Okay, you can give me any n, I can tell you exactly where to go. But this one, it's fine in terms of the previous ones. Okay, an plus 1 equals an plus n. What does that really mean? You get the next term by taking the previous term and adding the previous index to that number. So if I want, say, A100, I need to get A99, which means I need A98, which means I need A97. I got to climb the ladder, okay, instead of taking the elevator, okay? So I want to find the first 6 terms. So let's go ahead and run through this. We already given our seed, our initial condition, A1 equals 1, okay? Now, how do we get A2? Well, the next term is just the previous term plus the index of the previous term, okay? So we know that A1 is 1. 1 plus 1 is 2. Now let's take a look here. A3. Again, how do we get A3? How do we get the next term? The previous term, A2, plus the index of the previous term. Well, A2 is 2, and 2 plus 2 is 4. A4, we have A3 plus the index of the previous term, 3. 4 plus 3 is 7. Okay. A5, that's A4, the previous term, plus the index of the previous term, 7 plus 4 is 11. And finally, A6, we have A5 plus 5, 11 plus 5 is 16. So notice how, in order to get the next term, I needed all the previous terms before that. I needed all that new previous information. Now, the goal here is, well, not yet here, but we may want to find an explicit rule for this thing, okay? I may want to find an explicit rule. But take a look at this, right? Does this sequence appear to have a limit? Well, let's kind of investigate here, okay? Start with 1, then you go to 2, then 4, then 7. The gap gets a bit bigger, 11, then another bigger, 16. The next term is for clever, okay? 16 plus 6, 22. The gap's a bit bigger. So try to analyze these so-called common differences, okay? So let's just write out the list of the terms here. So we have 1, 2, 4, 7, 11, 16, and I'll go ahead and write the next one here, which is 22. If you look at the common differences, the distance between successive terms, okay, well, the jump from 1 to 2, that's 1. Then 2 to 4 is 2. Then 3. Then 4. Then 5. Then we see then 6. But then the difference of those differences, these second differences, they're the same. So you can show that you can actually get a quadratic out of this, okay? You can fit a quadratic to fit these points. But how does that help us with the limit? Well, notice that these terms get bigger and bigger. Okay, let's make a note here, okay, in this color, okay? The terms increase without bound, okay? We're going to take a note here that the gaps get wider. So is this going to settle on one number? No, if I take the limit, if I were to find a closed rule for this and took the limit, well, the limit would be infinity, okay? So the limit here, okay, watch Mean Girls, the limit does not exist. In fact, just because of that joke, we're going to go ahead and turn that to pink. The limit does not exist. The limit does not exist because these terms will increase without bound. Okay, so that's how we handle recursive sequences. Let's do one more here. Find the first 6 terms of this recursively defined sequence. So again, we're going to start with our initial condition, our seed, and then we're going to generate new terms out of this. So let's take a look here. Our seed, or initial condition, A1 is 1, and we generate the next term, an plus 1, by doing 3 minus the previous term. Well, let's just go ahead and write it out. So we have A1 is equal to 1. A2 is 3 minus the previous term. Last term was 1. So 3 minus 1 is 2. Okay. A3. We're going to have 3 minus the previous term. 3 minus 2. Okay, you see how we're just plugging in all the previous information? So 3 minus 2 is 1. Now let's look at A4. 3 minus, okay, take the previous term. 3 minus 1 is 2. A5. 3 minus 2 is 1. You probably see the punchline, right? We're just going to wiggle back and forth between 1 and 2. Okay. A6 equals 3 minus 1, which is 2. Okay. So you see how we're taking the result of the previous and putting that into our next term. Now, of course, you probably see again, just like with that sine of n pi over 2 in the second example, where we have just our terms are wiggling around. They're not settling. Okay. So this limits, this sequence oscillates. Okay, it oscillates between 1 and 2. And so, just like in Mean Girls, the limit does not exist. All right. So why are we harping so much about limits of sequences? Well, we're going to have a special word for that coming soon, okay? But this is just how you explore with sequences, okay? You generate some terms, right? Be it from a closed form rule or like these two on this page where you have a recursive rule. You have to generate a few terms. Explore, see what happens, okay? And then you'll probably gain some insight into how the sequence behaves. All right. So that's going to be the basics of sequences, all right? Coming up, we're going to see how we can take a rule, say a recursive rule, and write a closed form explicit formula for our sequence. So get your thinking caps on. I'll see you in the next one.